Yeah. So this is our lecture number 5, and we'll study in this lecture about one most important topic, which is the method of image. अगर आपने कभी नाम सुना हो तो आपको पता चल जाएगा. So basically, the table of content for today's lecture is. My voice is clear, no? You can hear me properly,
Yes,
right? Okay, okay.
yes, ma'am.
So, okay. Uh, So, this is the table of content for today's lecture. We will study method of image, what is method of image, how to form a image, and how to solve those questions. And then we'll calculate force and electric field in method of image doing the same procedure. And then dipole problem we will do with method of image. And then we will also apply some boundary conditions in our method of image, and at last we will do some examples as well. So what is method of image? Basically, the method of image is a procedure to solve a problem in which we use any conducting plane or any grounded plane or any mirror. So if a charge is nearby any conducting plane or any grounded conducting plane, then this problem we can't solve by using Coulomb's law or Gauss law, because they have some specific restrictions to solve. So the method we use to solve these types of problem is method of image. Basically, the method of image is the formulation or the recipe to solve the Laplace and Poisson equation. Okay, so method of image is basically for we'll do for multiple images or for one images or for two images and so. So we are moving ahead. The first thing which we will discuss is solving the Laplace and Poisson equations by sleight of hand. Sleight of hand means with an ease, means the easiest way. So if we want to solve Laplace and Poisson equation, we talk about the boundary conditions. And if the boundary conditions are on that conducting plane, if we will apply the boundary conditions on that conducting plane for a charge near the conducting plane, then the problem becomes complex, and we don't want so. So to make an ease of that problem, to solve with an ease of that problem, we use this method of image. So the method of image today is very powerful technique for solving electrostatic problems involving charge in conductors. And method of image technique eventually will use separation of variables. So the separation of variables, you know, because you have studied about it in your graduation. And uh, there will be some examples related to multipole expansion. So what is this multipole expansion? Basically, this is one another topic, multipole example, which we should study whether preparing for NET exams, but due to the lack of time and due to the restriction of number of lectures, we can't provide you all the topics in this way. So the multiple expansion we will study only for the method of images. Okay, so Fermi used to say, when in doubt, expand in a power series. This is multiple expansion, means if we have any problem, if we have any problem related to multiple charges on in front of a screen. So what we can do, we can say that problem that it is a multiple expansion problem. And what we can do, we can expand all the terms in a power series. In yes, is someone saying something? No. Okay. So yes. Okay, moving ahead. So we will study about multiple expansion too. So basically, this is the introduction to the method of image. Don't need to read all this stuff. Just look at this picture. There is a conducting plane, the red one. It is a conducting plane, and the plane is grounded. What do you understand by the plane is grounded? The plane is grounded means all the charges on the surface are now we have grounded them to any point in the earth, so that there is no surface current. And if there will be a surface current, then we can't use the method of images. So we have to basically use any grounded conducting plane, because we don't want any surface current or any surface charge. So there is a grounded conducting plane. From this plane at the distance d, there is a charge q. So we can say the charge and the plane, the charge is in z direction with respect to this plane. So this is when we will introduce the Laplace and Poisson's equation for this type of problem. We will introduce some boundary conditions. You guys know that. So the boundary conditions will be like as the plane is grounded. Okay, so there is no surface current. If there is no surface current, then voltage is obviously zero. So the first boundary condition is V equals to zero. The voltage is zero. What will be the second one? As the charge is in z direction, the direction of the charge with respect to this plane is in z axis. That is why the electric field components Ex and Ey should obviously be zero. So if Ez have some value, then Ex and Ey will be zero. So this is the basic introduction of method of image, and we will do this and we will use that situation, and we can continue as we can find out the potential, we can find out the force, we can find out the electric field, and so on. Many things. We can also find out the energy. We can also stimulate with the Poisson equation, so that we can find out the charge density and many more. Anything you can find out using this method of image. So the previous problem is here. What we can do to solve these types of problems, we will make an image charge. Here is the original charge Q. We will put an image charge minus Q below to this conducting plane. Okay, the question was this one. Okay, this one was your problem. And what you will do to solve this problem, you will make an image of this charge. This is a charge and this is the image of that charge. As the charge is situated at distance d above the plane, then this image charge
Hello,
will
ma'am.
also be, yes,
Ma'am,
yes,
voice is become low. Voice is
okay.
low.
Voice is coming low. Okay, I'll try to speak
Yes.
aloud. Yeah, is it clear now? Is it clear now? Can
Okay.
I
Okay.
speak in this manner, or I should raise much more the voice? It is clear, I think, now.
No. Okay, ma'am. This is
Yeah.
yes.
So let me. I have to stop the presentation if I want to raise my voice now. Just check audio settings. या वॉल्यूम मैक्सिमम कर देते हैं, चलो ठीक है. Okay, so we have to make an image charge. We will make an image charge below to this plane. Is it clear now? Is the voice is clear?
Yes, ma'am. Clear.
Yeah, okay. So below this conducting plane, there we will put an image charge. Obviously, it will be in opposite direction. Hello?
Yes, ma'am.
हाँ हाँ, मैं मेरी क्लास चल रही है, मैं थोड़ी देर में करती हूँ फोन. Yeah, so sorry, there was a call, so we will continue. Yes, so it is a negative charge we will put. Okay, the amplitude of charges we will put same, but the direction of charges or the magnitude of charge will be opposite. The sign will be opposite, obviously, and the direction will be opposite. If the original charge was in z direction, then the image charge will be in minus z direction. Okay, so if we have to find out the potential, so the potential we can calculate directly. So the potential will be S y z. Why I am writing this? Because we are considering only z, and we are writing it in cylindrical coordinates. We can write in any type of coordinates we can use. Okay, so if we are considering some infinitesimal distance S, then we know that potential V is equals to Q over kq over r. So this is under root of distance, basically the r. So if we want at any point, if we want at this point, I am considering a point here. So the direct distance, okay, this is your d, okay, this is your whole z. So this distance, what this distance will be? Z minus d, obviously. And if we can put this as s, so it will be under root s square plus d square. Okay, so we can write this as this one. For negative charge, we can write this. When we will do examples, you will get to know how we can solve these types of problems. Okay, so if we once calculate the potential, then we can also calculate the electric field. So the electric field, whether we are doing some phi dependence, then we know that electric field is equals to minus delta V. In cylindrical coordinate, we will write it as del V over del S S cap plus 1 over S del V over del phi phi cap plus del V over del Z Z cap. Okay, so this del V over del phi phi cap, we don't know this thing. We know only two directions, S and Z. So we will do this with respect to this V, and we can find out these four terms. Okay, because electric field is perpendicular to z equals to 0 plane, what we will do, we will just put this value z equals to 0. So whenever z is, wherever z is, we will put this z equals to 0, and we can get only single term, that is E s phi 0 equals to minus 2q d over s square plus d square is to the power 3 by 2. And if we want to calculate the sigma, surface charge density, then we are using the Poisson equation, E perpendicular above 2 pi. This is the formula for sigma. You can, this is the direct formula. We can derive this formula too using Poisson equation and extracting some boundary conditions, applying E parallel and E perpendicular. So we can get this, either you will remember this formula directly, sigma equals to E perpendicular over 4 pi. If we put this, we get this, or sigma. Okay, so there was one problem. This is another problem. This was our calculation solution, what we were doing in method of images. We have done with this stuff. We have put a charge positive q, then a charge negative q in method of images at same distance d. So now, if we are changing the problem, we have changed the whole system now. So if we are changing the system, we are altering the boundary conditions. Now the boundary conditions will also change. Okay, so for, and the second one, the uniqueness problem will also be followed, that for every problem there is a unique solution. Okay, so this system is obviously equal to this one. We have altered this now into this, we have converted this into this now. So if some boundary conditions were for this situation, we have to convert all those boundary conditions for this situation too. Okay, so what we can do, we will consider one point, as I have told you earlier too, we will consider one point, and then we will see this plane as a mirror, because method of image means forming an image. So if this is a mirror, then using the mirror ray diagram, if one ray is coming from here to here, it is reflected to here, and if we are extracting to it backward, then one image we will get on this point, obviously. So this conducting plane is behaving as a mirror. So this is the real theory in method of images. So the solution for the images is only the same as that for the conductor. In the region outside the conductor, means we want to say that if we are talking about any point inside the conductor or the same point outside the conductor, we will form the same image if the charge is same, but we will get different solutions because we have to follow the uniqueness theorem. So this is the first CVET for method of image. The second one is, in particular, the potential energy of charge plus conductor arrangement is quite different from the charge image charge combination, because the field is finite for the latter in locations where the field of former is zero. Okay, you can understand these things. And the third one is also simple. So okay, this is one problem from your Griffith's book. I have shared the book of electrodynamics in the WhatsApp group also. So please guys, download that book if you don't have that book, and if you have that book, then there is a chapter in Griffith, chapter number 3, that is called the method of images, and there are more than 60 to 70 problems of method of images. So just try one by one questions to calculate the things which are asked on those questions, and tell me whether you are able to solve those questions or not. I can eventually provide you the solutions of those problems too. So please guys, you will solve those, and this is your example 3.2, problem 3.7, means both are the same, but in example 3.2 and in problem 3.7. So from your chapter 3 of Griffith, there was a problem. A point charge q is situated at a distance z from the center of a grounded conducting sphere of radius r. This is your sphere, which is grounded conducting sphere. A point charge q is situated at z distance. We have to calculate the potential everywhere. Find the induced surface charge on sphere as function of theta. Integrate this to get total induced charge and calculate the potential energy of system. So we have to calculate three things, and one by one we will calculate. So the first one, we have to calculate the potential everywhere. So everywhere means at this point P, at the surface, inside the sphere. There are three points. Okay, and we will apply some boundary conditions also. So we will modify this problem as this one. This is our method of image, the method we will use. Okay, we will consider this sphere as a mirror, and this charge which was situated on the distance z now, the image charge will be on this point. Okay, this is the way to solve the spherical problems, the symmetrical problems. Okay, the plane problems we have discussed. Now we are discussing about the spherical or symmetrical problems. So this is the sphere and or the conductor in spherical shape. So we will put an image charge at this point, which will be from the center z dash distance. From the center it is z dash distance. Okay, and this one is d dash, because this was your d, so this one is d dash. On the surface, we are saying that this is a grounded conducting plane. Grounded conducting plane means v is 0, obviously. So on the surface, v is 0. So one thing we have calculated for the grounded conducting plane, v is 0. Vp, so potential at point P, this is your point P. you can see in this diagram, this is your point P. So this point P is on your surface now. This is your point P. Okay, so as this point P is on the surface, so you can write directly as equals to 0, or you can calculate to for q charge, for q dash charge. Okay, so from here you can get q dash, the value of q dash. Now vq is also equal to 0. Where is that q? The q is not given here now. Basically it is your vq, this point. Okay, q. So this is also 0, so you can calculate q dash from here also. Okay, so there are two values of q dash, put them equal, you will get an equation. Rearranging them, you will get this type of result. So these are the direct relations you will remember. What is that? If we are solving some problems for point charge outside a grounded sphere, then the image charge will be situated at the distance equal to r square over z. Z is the original distance of the original charge, and the image charge q dash, the amplitude of the image charge will be minus qr over z. This was the direct question which have come into your exam in, I think, net June 17 or 18. I don't remember exactly, but the direct question was from here. Okay, so thus now consider an arbitrary point on sphere P dash. Now we are considering any arbitrary point which is situated on theta angle. So we are considering the point P dash, that is arbitrary point. We are considering here. We can consider here. We can consider here. We can consider here. Anywhere we can consider. But in your Griffith's book, it is here. So for this point P dash, the distance will be like this. D. D dash will be this one. Just put the value of D dash and Z dash. I am putting the value of this Z dash here and solving. Vp dash will be q over d plus q dash over d dash. Just putting these values, and I am getting finally 0 because the point was on the surface now. So eventually we will get the value 0. So Vp dash will be also 0. So the same procedure the Griffith has followed. So you can also watch in the book. The same procedure is there. I will share this PDF also. Okay, so potential for a point charge in a ground conducting plane. So we are getting this type of potential, and the charge density we can find out. You know the recipe. So del V over del R you can calculate, and then sigma you can calculate. Okay, if you have to calculate total charge Q, then which formula you will use? So this is the formula. I have never told you this formula earlier before. So the total charge Q will be equal to integration sigma r square sin theta d theta d phi. Why this r square sin theta d theta d phi? Because sphere is it. So we will use spherical coordinate, and in this spherical coordinate the area content is r square sin theta d theta d phi. Okay, so just solve this integration and you will get total charge q as minus qr over z. What is that? This is the value of image charge q dash. So the total charge q will be equal to the image charge, which will goes to 0 as z goes to infinity. If the distance is infinity now, the total charge will be 0. And we can also calculate the force between q and q dash, the formula you know. And we can also calculate the work. If we have calculated the force, then we will calculate the work also. Okay, so okay, this is one simple example. This is again from the book of Griffith. A positive point charge q is located at distance d1 and d2 respectively from two grounded perpendicular conducting half planes. There are two planes which are perpendicularly set. A charge is between these planes. it is from this plane it has the distance d1, and from this plane it has the distance d2. Okay, determine the force on Q caused by the charges induced on the planes. So we have to calculate the force on this charge. So obviously we have said that this is a grounded conducting plane. So watching this word, we will start solving by method of images. So one image charge will be this side, one image charge will be this side, and we have to make always a symmetry, because without any symmetrical shape we can't solve any problem. So we will also induce a charge on this side. Okay, the charge will be having same sign, but the image charges will have different signs. Okay, so if we will talk about two conducting planes, we will always follow the symmetry. So now there are four charges, and you know from Coulomb's law you can solve this type of problem. Just calculate this problem. The F will be F1 plus F2 plus F3. We have calculated these types of problems now. So just in the method of image, what we have to do, we have to make images. Now we have to think only that where we will plot image, and at what distance we will plot image, and how many images we have to plot. Just we have to think this thing, and all this stuff is really easy. Okay, one another, line charge and parallel conducting cylinder. We have talked about one plane, we have also discussed on two planes, we have also discussed about sphere. Now we will discuss about conducting cylinder. Okay, we have a conducting cylinder and we have a line charge. Okay, so there is a point P and the line charge having some charge density. Obviously, the point P is from the center at d distance. So just we'll follow the method of spherical symmetry, and we can induce a image, an image inside that symmetry at some d dash or di distance. Okay, but for spherical shape, the values of d dash and q dash were different, and in the cylindrical shape we can write rho I equals to minus rho I. This is this one difference between sphere and cylindrical shapes. The rest of is same. We can calculate electric field, and we can then calculate the V. Okay. Okay. So two parallel conducting cylinders of same radius. If we have two parallel conducting cylinders of same radius, then what we will do, we will just put the value of that voltage, then we can get the relations between two radius. Then we will put that for V1 and V2, like we will generalize, and capacitance we will calculate, and just putting the values we can get this stuff. Okay, this was not an important slide, that is why I was not going to put it here, but by some mistake it is here. Okay, now coming to some really important aspect of that method of images, we have discussed about various types of problems we can solve using method of image, like for a single plane, for two planes, for sphere, for cylinder, like for any symmetry we can use this method. But there are some boundary value conditions. I have told you earlier too that we have to follow all those boundary conditions. So there are some problems, and we have classified those problems as the classification of boundary value problems. And the first one is Dirichlet problem. What is that Dirichlet problem? In which the value of potential is specified everywhere on the boundaries. We have to calculate the specific potential everywhere on the boundary. Like if one boundary I will set, at x equal to a. A is my first boundary. So firstly, I'll calculate the potential on that x equals to a. Then I can move ahead. This is the first boundary value problem. The second one is Newman problems. These are the scientist names. Newman and Dirichlet was two scientists. Okay, Newman problems. What are those Newman problems? In which the normal derivative of potential is specified everywhere on the boundaries. Means the normal derivative means the perpendicular part, the potential having some derivative, and the perpendicular part of the derivative we will calculate for those boundary condition. Like we will calculate what we will calculate the v perpendicular and at any boundary condition like dx I am putting here. So if x is equals to a, then what we will do, we will just limit that value x equal to a. Okay, so this is your Newman problem. Third one is mixed boundary value problems. Mixed boundary value problems means we will calculate the potential as well as the derivative of the potential. Both the things we will calculate, then we will move ahead. Okay, so this was those were some boundary value problems we can do with that method of images. And so we can get some results also. Okay, just I have to stop sharing because I have another slide to show you guys. So just let me check. Just 1 minute. There is a PDF. I have to show you guys that PDF. I will upload on with this lecture too on the drive, and from just reading that PDF, you can get all the stuff related to this method of image. Let me find out where it is. Yeah, so you can share me if any query you have, any question you have regarding this lecture till now. Just share me your queries or questions so that we can move ahead. Yes?
No doubt, ma'am.
No doubt. Okay.
No doubt.
So have you seen the assignment one I have shared? Have you seen, guys? Please do
No,
Yes,
that
ma'am.
ma'am.
assignment. Yes, yes. So, yeah, I will share now. So please, guys, do that assignment so that you can get the maximum stuff of that electrostate. Okay. So we were talking about the boundary value problems in electrostatics now. So there are some specific method of images in which we can use those Dirichlet, Newman and mixed boundary value problems. So what are those symmetries? So one symmetry is on your screen. You can see if we have undetermined symmetry, like we don't know the shape. Okay, so if we don't know the shape, how we will solve the problem? How, where we will put the image charge, from where we can get the potential? So these types of problems are classified in the complex problems in electrostate. So these types of problems we can solve using Dirichlet and Newman boundary conditions. So this is the recipe and the conducting sphere. The same, all the things are coming. You can see green function we can use. Or I am not going to teach you about the green function. obviously. So this is the important PDF I will share with you guys, from where you can get all the things about green functions. And obviously this PDF is a chapter from the book J.D. Jackson, Introduction to Electrodynamics by J.D. Jackson. So this is a chapter of that book. From this chapter you can get the maximum stuff related to your exam. If you guys are unable to understand any of the concept in this PDF, please let me know. Please share your queries so that I can bring the solutions for you guys. Okay. This is the PDF, and it is a beautiful PDF. And easiest way we can understand all the things. Like look at these diagrams. Beta depend rho dependent variation of surface charge density for various corner angles. If we have two conducting planes, one is here and second one is here, and both are inclined to each other at beta equals to pi by 4. The angle between the both is pi by 4. Then the charge density will be rho q. Okay. And if beta equals to pi by 2, this is rho. If beta equals to pi by 2, rho equals to 1, and this one. So these are some beautiful images in this PDF. So I'll share this PDF. Okay. So I have not put some questions regarding to this net GRF, regarding your problem of net GRF, but we will do some problems in our next lecture. So yeah, I'm gonna stop here. If you want to ask me anything regarding this subject, you can ask. Anything if you want to ask, you can ask. You can share your views.
Ma'am,
Yes, Hasmukh.
ma'am, in electrodynamics, question is very mixed up in
Yeah.
various
Not in
topics, and
electrodynamics.
so
It
how
is
can we
only,
solve
yes,
easily?
yes. Not in electrodynamics. It is only in electrostate. Because when we will start our magnetostate portion now, from next lecture, we will start magnetostate. So from those lectures you can get, like electrostate is more confusing, magnetostate is quite different, it is easier. And the third portion when we will study about Maxwell equations, those are even easier. So electrostate is quite confusing because there is a lot of stuff in electrostate, a lot of stuff, a lot of books to follow to grasp all the electrodynamics, and we have no time for doing that. There, it takes a hard work of a whole year, like 12 months, at least 12 months to study well about electrodynamics. So please don't go inside that electrodynamics. Just find out some easy problems, do those problems. If we have 40 marks of electrostate in our paper, like we are getting 40 marks of electrodynamics portion, then at least we can solve 25 marks. We have to prepare only 25 marks. Okay. So just set the target of 25 mark and do your preparation, like no, even half marks no one can cut. You will get 25 out of 25. You have to follow this one, because you can't get 40 in electrodynamics, not in a limited time. No, not possible. It is an comparatively hard subject, I must say. Yeah. Anything else? just
No, ma'am.
just do those assignments na, Hasmukh. Just
Yes.
do assignments. The first assignment I have shared now, those are only GAT problems, and those are easy problems. Start with those easy problems. If once you can get confidence now that I am able to solve these problems, Then in the next assignment, I will share some average problems also, and in the next assignment, we will do some hard problems also. So just step by step, we have to study.
Sure.
Yeah. So those are all GAT problems, which assignments I have shared now. Assignment 1, soon assignment 2 I will upload. I will upload some question of method of image 2, and that PDF also I have shown you, that PDF also I will upload. If you want anything, any study material from my side, you can message me. You can put your message on our WhatsApp group. Okay. So all for today. Thank you guys.
Thank you, ma'am.
Okay.